So, if you just opened a brand new vacuum-sealed spool of PETG, left that little silica gel packet sitting on your desk, and, immediately hit print on your machine, well, you have probably already ruined your part.
Yeah, it is a really harsh reality to face. I mean, so many people treat that vacuum seal as this ultimate guarantee of absolute perfection. But the physics of advanced polymers, they just do not care about the plastic wrapping.
Right. It is like the classic rite of passage in 3D printing.
Yeah.
You spend months mastering basic PLA, you get your first layers looking absolutely flawless.
Yep. Your printer is humming along like a Swiss watch.
Exactly. And then you decide it is time to upgrade. You need a part that can survive sitting in a hot car or maybe something with real mechanical strength. So you load up your very first spool of an engineering filament like PETG or ABS or maybe even nylon.
And that is where it all goes wrong for most people.
It really does. You hit print using your trusty PLA workflow and suddenly you are staring at this hairy, stringy, blobby nightmare. It completely ruins the print.
The immediate reaction is usually just panic. You feel like you have suddenly forgotten how to use your own machine. But the printer is doing exactly what you told it to do.
Which is the problem, right?
Right. The core issue is that you are treating a completely different chemical polymer as if it were just heavy-duty PLA.
And that brings us to our mission today. We are doing a deep dive into two really comprehensive sources from Printera 3D. We have a Monday Hub article completely dedicated to troubleshooting stringing in engineering material.
Yeah, that one is super detailed.
It really is. And we are pairing that with a Thursday support piece that covers the intricacies of flow rate calibration. Our goal today is to give you, the intermediate FDM printer hobbyist, the next level decision framework for getting clean, dimensionally accurate prints.
And the central theme across both these sources is incredibly clear. Success in materials like PETG, ABS, ASA, and nylon requires attacking moisture and flow rate together.
Yeah.
You simply cannot just copy a PLA recipe.
So let's unpack that. To really grasp why the old PLA profiles fail so spectacularly, we have to look at the physical properties of the plastic melt itself.
Yeah, Bambu Lab actually has some great documentation in their materials guide that breaks this down really nicely. They explicitly point out that PLA flows easily. It is, highly cooperative inside the HOTEN.
But when you switch to other materials, the fluid dynamics change entirely, right?
Completely. ABS and nylon are physically denser. PETG is famously sticky and viscous. TPU is highly elastic. And then you have composite filaments.
Like the ones filled with carbon or glass fibers.
Exactly. Those add abrasive physical chunks into the fluid mix. So the way the plastic behaves under pressure and how it cools as it leaves the nozzle is just a completely different ballgame.
Let's talk about temperatures for a second. The source notes that ABS and ASA print at roughly 240 to 260 degrees Celsius. That is massively hotter than PLA.
Right. It is a huge jump in thermal energy.
So does that higher ambient and nozzle temperature mean the melted plastic stays liquid for much longer after the extruder actually stops pushing?
That is a huge part of the problem. When the extruder motor performs a retraction, pulling the filament backward to relieve pressure, the plastic in the melt zone doesn't just instantly freeze.
Because of the retained heat.
Right. Because ABS and PETG retain heat differently, they stay in this semi-liquid, gooey transition state for a much longer window.
My absolute favorite way to visualize this physics problem is thinking about the difference between piping hot frosting versus warm caramel.
Oh, that is a great analogy.
Yeah, the hot frosting, which is our PLA, stops flowing almost the exact second you stop squeezing the piping bag. It shears and breaks cleanly. But the warm caramel, which represents our PETG or ABS, stays gooey.
Right. And when you pull the bag away, the caramel does not break.
Exactly. It just pulls these long, frustrating microscopic strands along with it.
To build on that caramel analogy, think about what happens when you try to pull a string of warm caramel apart really fast. It does not snap. It just stretches into a thinner and thinner web.
Oh, wow. Yeah, that makes perfect sense.
This is exactly why a lot of people fail when they try to fix PETG stringing by simply cranking up their retraction speed in the slicer. High-speed retraction does not break the surface tension of a sticky, viscous polymer.
It just pulls a spider web.
Right. It just rapidly pulls a very thin spiderweb-like string across your travel move.
I have to admit, my initial thought when I see a stringy PETG print is absolutely to just twist dials in the slicer. Increase retraction distance, speed up the travel moves, drop the temperature.
Everyone does that. But according to the Printera 3D troubleshooting guide, jumping straight into slicer settings is jumping the gun. We really have to figure out exactly what kind of defect we are looking at first.
Right. Is it a true flow and retraction problem, or is it a moisture problem masquerading as one?
Moisture is the great deceiver in 3D printing.
Hmm.
Materials like PETG, nylon, PACF, ABS, and ASA are all highly hygroscopic. They actively absorb moisture from the surrounding air.
And they don't just get wet on the surface, do they?
No, not at all. The water molecules actually chemically bond within the polymer chains of the filament itself.
Well, I have to push back on this idea of new filament being wet. This goes back to my point at the very beginning of the deep dive. If I unseal a brand new factory spool straight out of the vacuum sealed bag, and it has the desiccant packet inside, I mean, the manufacturer dried that, right?
You would think so. The assumption makes sense intuitively, but the manufacturing reality is very different.
Why on earth would I hear popping sounds coming out of my nozzle on a totally fresh spool?
Well, during production, the freshly extruded filament is incredibly hot. To solidify it quickly so it maintains a perfectly round shape, factories run the filament through these massive, long water cooling baths.
Oh, I see.
And even though they use high-powered air knives to blow the water off before schooling, residual moisture frequently remains trapped deep inside the plastic. When they vacuum seal it, they're often just locking that residual factory moisture inside the bag with the plastic.
So you are basically buying pre-moistened filament. That is wild. What actually happens inside the Hoten when that trapped water hits a nozzle heated to 250 degrees Celsius?
It is violent. Water expands to roughly 1,700 times its original volume when it flashes into steam.
Wait, 1,700 times?
Yeah, 1,700 times. So you have a microscopic droplet of water trapped inside a confined metal nozzle mixed with thick, molten plastic. It instantly vaporizes. That massive sudden expansion of steam creates a huge pressure spike inside the hot end.
And the plastic has nowhere else to go.
Exactly. It literally sputters and shoots the molten plastic out of the nozzle.
Like microscopic popcorn popping inside the melt zone.
That is a perfect way to describe it. And that sputtering happens constantly. When the printer makes a travel move across open space, that steam pressure forces a blob of plastic out, drawing a string with it. This is why moisture perfectly mimics a bad retraction or flow setting.
Okay, so we need a very clear decision guide here. If you are printing PETG nylon or, say, a carbon fiber-filled nylon, and your prints are showing hairy strands, or maybe you hear those subtle popping or hissing sounds at the nozzle.
Or even if your temperature calibration towers have fuzzy textured surfaces.
Right. In all those cases, you need to skip the flow tuning entirely. You must dry the spool first.
Tuning flow on wet filament is a complete waste of time. The steam pressure is randomly altering your extrusion volume second by second. It completely invalidates any math you try to apply.
Okay, so once you rule out moisture, then you can start looking for true flow defects.
Yes. You run a flow rate calibration when you see consistent structural problems. If your top layers have blobs pushing up or the physical dimensions of the part are noticeably oversized, you are looking at over-extrusion.
And under-extrusion is the opposite.
Right. If you see gaps between your outer perimeters or the top solid infill looks cracked and doesn't fully connect to the walls, you are dealing with under-extrusion.
But before we touch the flow settings to fix those gaps or blobs, we cannot ignore the physical hardware variables. The Printura 3D source notes you only run a flow calibration on a printer that already has its temperature, Z offset, and pressure advance dialed in.
That is a really crucial point.
I mean, Z offset makes sense. If the nozzle is plying too close to the bed, it forces plastic up into ridges. That looks exactly like over-extrusion, but it is actually just a leveling issue.
But what about pressure advance? What is that actually doing in relation to flow?
Pressure advance is critical when we talk about engineering materials. We established earlier that these polymers act a bit like a rubber band or a spring when they are melted.
Because they are so viscous.
Exactly. When the extruder motor pushes the solid filament, pressure builds up in the nozzle. When the motor stops, that pressure takes a moment to release. If the printer doesn't account for this, you get huge bulging corners because the plastic keeps oozing as the tool head slows down to turn.
Ah, okay. So pressure advance fixes the timing?
Right. It is a firmware algorithm that preemptively retracts the filament just a tiny bit before a corner and pushes a bit extra during acceleration. That keeps the actual nozzle pressure perfectly constant.
So if your pressure advance is wrong, your corners will look like terrible flow issues, but the middle of your lines might be totally fine. Which is exactly why you isolate the variables. Get the bed level, get the temperature right, get the pressure advance set. Only then do you calibrate flow.
Let's transition to the non-negotiable first step we teased earlier. Before we dive into the dense math of slicer settings, we really have to talk about how to actually fix the moisture issue.
Yes, this is the most important part.
If there is a single actionable takeaway you apply to your printing workflow today, it is this. Before touching retraction, before tweaking flow, take your spool of PETG, ABS, ASA, or nylon and dry it at the manufacturer's recommended temperature for at least 6 hours. Then, and only then, rerun your stringing test.
The time and temperature matter immensely here. You can't just guess. PETG usually needs to sit around 65 degrees Celsius. ABS and ASA take slightly more thermal energy to release their moisture, usually requiring 70 to 80 degrees Celsius.
And you need a proper device for this.
Absolutely. You need a dedicated filament dryer or a repurposed food dehydrator that can hold those temperatures steadily and safely.
And it has to actively vent the moisture out. Just trapping the spool in a warm box does not pull the water out of the polymer matrix. Definitely do not just put it in a kitchen oven.
Oh yeah, never use a kitchen oven. That is a recipe for a melted spool in a ruined oven.
Right. So, all right, let's say the filament is bone dry. Our Z offset is perfect. But we still have daps in our top surface, meaning we have a true under-extrusion issue. Now we have to navigate the slicer software to fix the flow. And the terminology across the industry right now is completely fragmented.
It creates so much unnecessary confusion. The setting we were talking about alters the baseline amount of plastic the slicer asks the extruder to push. If you were using PrusaSlicer, this core setting is called the extrusion multiplier.
But if you open up Bambu Studio or OrcaSlicer, that exact same variable is labeled flow ratio.
Right. It is the exact same underlying math, just a different name.
Okay, so extrusion multiplier and flow ratio are doing the identical mathematical operation. But it gets a little more complicated because almost every printer has a physical screen or a web interface that also has a flow percentage slider. How do those interact?
They actually multiply against each other. The total volumetric flow that actually exits your nozzle equals the firmware flow multiplier, which is the setting running on the printer itself, multiplied by the slicer's extrusion multiplier.
And on top of that, there is a specific G-code command, right?
Yes, the M221 command. That can be injected into your startup script to override that firmware value at runtime.
Think of it like having a software volume slider on your computer, like in Spotify, and a physical volume knob on your desk speakers. They multiply together to give you your total audio output. If your Spotify slider is set to 50% and your physical desk speakers are turned down to 50%, you are only getting 25% of the total possible volume.
That is a brilliant analogy. Taking that audio analogy further, if you spend an hour carefully tuning your slicer's flow ratio to 0.98 for a tricky spool of ASA, but you forgot that you manually dialed back the printer screen to 90% during a previous failed print, well, your total flow is going to be significantly under-extruded.
You have to ensure the firmware multiplier is resting at 100% or a 1.0 factor before you start tuning in the slicer. Otherwise, your baseline is completely skewed.
Exactly. You always have to check the screen first.
So how do we actually find that perfect 0.98 or 1.02 number? The Printara 3D articles detail two distinct paths for flow calibration. There's the highly precise mechanical method and the visual method. Let's start with the precise one.
The precise method relies entirely on physical geometry and calipers. You generate a calibration square in your slicer, but you set the walls to be just a single perimeter thick. You disable the top and bottom solid layers, and you set the infill to 0. The printer essentially just prints a hollow single wall box.
And then you let it cool down, take a micrometer, and measure the actual physical thickness of that single extruded wall.
Right. You have to use a high-quality micrometer, not just cheap plastic calipers, because you are measuring fractions of a millimeter. If the slicer was programmed to print a line width of 0.45 millimeters, but your micrometer reads 0.48 millimeters, the printer is pushing too much plastic.
It is basic math at that point.
Exactly. You take the expected width, divide it by the measured width, and multiply that by your current flow rate. That spits out your new mathematically tuned value.
That sounds incredible for printing highly engineered mechanical parts that need really tight tolerances to fit together. But what about the visual method? For the average hobbyist making functional brackets or display pieces, measuring microscopic plastic walls feels a bit tedious.
The visual method is much more approachable, and it is actually built directly into slicers like OrcaSlicer as an automated test. The software generates a series of small, flat test blocks on the build plate. Each block is automatically assigned a slightly different flow ratio.
And they all print simultaneously.
Yes. When they finish, you take the plate off, and you just shine a light across the top solid layers.
You're basically looking for the Goldilocks block. You want the top surface that is perfectly smooth. If it has rough, shiny ridges where the nozzle plowed through excess plastic, that block is over-extruded. If there are tiny gaps between the diagonal infill lines and the outer perimeters, that block is under-extruded. You just pick the number printed on the smoothest block.
It is very straightforward. But there is a lingering myth in the community I want to address regarding these test blocks. A lot of older guides stated that these calibration sweeps must always cover a strict range of 90 to 110% flow.
I have read those exact guides. They treat that 90 to 110 range as absolute gospel.
The data and modern slicing algorithms just do not support that as a hard rule anymore. Depending on the material density or whether the slicer is doing a coarse pass versus a fine-tuning pass, the software might use entirely different scaling parameters. So don't freak out if the numbers look a little different. Right. You do not need to panic if the automated test suggests a range outside that old standard. Just trust your eyes on the final surface finish of the top layer.
That makes a lot of sense. Let the visual evidence guide the math. But we also have to recognize that the printer's hardware is not a static environment. Over time, physical wear and tear can completely silently alter your flow rate.
Especially when you are dealing with engineering filaments, which goes right back to the Bambu Lab documentation noting how abrasive composite materials are. Materials filled with chopped carbon fiber, glass fiber, or even glow-in-the-dark particulates act like liquid sandpaper flowing through your hot end.
If you push a spool of carbon fiber nylon through a standard brass nozzle, it slowly chews away the inside of the bore.
It is brutal on brass. A perfectly machined 0.4 millimeter brass nozzle can easily be hollowed out into a messy 0.5 or 0.6 millimeter hole after just a few rolls of abrasive filament.
Which means that carefully calibrated flow ratio you calculated last month is now forcing plastic through a massively widened hole.
Yep. Your pressure drops, your lines get sloppy, and your consistency is completely ruined. Hardened steel or ruby-tipped nozzles are absolute requirements for these materials to keep your volumetric flow math accurate over time.
And it is not just the nozzle, is it? The entire physical layout of the extruder fundamentally changes how we control stringing and pressure. A direct drive setup, where the extruder gears sit directly on top of the hot end, has a very short, tight path for the filament. It responds almost instantly.
Right, which means direct drive systems typically only need 0.5 to 2 millimeters of retraction distance to successfully drop the pressure.
Contrast that with a Bowden setup, where the extruder motor is mounted on the frame and the filament has to be pushed through a long PTFE tube to reach the moving hot end. The Printer 3D guide mentions Bowden setups need anywhere from 2 to 6 millimeters of retraction. Why does pushing the plastic down a tube require so much more pullback?
It comes down to mechanical slack and tolerance. The inside diameter of a PTFE tube is slightly wider than the 1.75 millimeter filament. When the motor pushes the filament forward, it bucks and bends slightly inside the tube.
Kind of like trying to push a wet noodle.
Exactly, it compresses. When the motor stops and reverses for a retraction, it first has to pull out all that slack and unbend the filament before the pressure at the actual nozzle tip even begins to drop.
Oh, I see.
That physical hysteresis is why Bowden systems need massive retraction distances compared to direct drive.
I have a very practical question that bridges the math and the physics here. Let's say I spend my entire Saturday afternoon drying my ABS, leveling the bed, tuning pressure advance, and doing a meticulous single-wall micrometer calibration.
Sounds like a fun Saturday.
Right. So I find my magic flow number using a high-quality slow profile running at 60 millimeters per second. But next week, I need to bang out a rapid structural prototype, so I switch to a 200 millimeter per second draft profile. Does my perfectly calibrated flow ratio still hold up at those speeds?
The short answer is no, it does not.
Why not, though? I mean, the slicer knows how much plastic to request. Shouldn't it just scale linearly?
You would think so, but it is because polymer melt dynamics are incredibly dependent on thermal residence time. Plastic does not conduct heat instantly. When you print at 60 millimeters per second, the plastic spends a long time inside the heater block. It melts thoroughly, becoming very fluid.
Okay, that makes sense.
But when you crank the speed up to 200 millimeters per second, the plastic is just flying through that heater block. The core of the filament might not fully reach the target temperature.
So you are trying to push a colder, thicker, more viscous plastic through the exact same tiny nozzle.
Exactly. The effective viscosity increases, which creates massive back pressure against the extruder gear. The gear might slip slightly, or the motor might skip microscopic steps. So a flow ratio that delivered flawless layers at a slow speed will almost certainly result in under-extrusion at high speeds.
Because the physical system simply cannot melt and push the volume fast enough to keep up with the math?
Right. The takeaway is you have to calibrate for the specific job you want the printer to do, not just establish a generic baseline for the spool. If the final part requires rapid prototyping speeds, you absolutely must print your calibration blocks at those rapid speeds.
Calibrate the system as it will actually be used in production.
Exactly.
Let's summarize the journey here. Moving away from standard PLA to engineering materials like PETG, ABS, ASA, or nylon is not just a simple temperature bump. The thermal properties and fluid dynamics are fundamentally different.
And your very first line of defense is always attacking moisture. You have to dry the filament for at least 6 hours at the manufacturer spec. Do not rely on the factory vacuum seal.
And do not waste your time tuning slicer settings until you are absolutely certain you aren't fighting microscopic steam explosions in the hot end.
Once the moisture is removed, then you diagnose the actual defect. You differentiate between stringing and true extrusion issues. You ensure your Z offset and pressure advance are locked in.
You understand how your slicer's flow ratio or extrusion multiplier interacts with the printer's firmware. And finally, you run your calibration sweeps at the exact target speed you intend to print your final part.
It is a deliberate, systematic approach. You have to eliminate the variables one by one.
I want to leave you with a final, slightly provocative thought based on what we discussed about hardware wear. We know that abrasive composite filaments slowly hollow out the internal diameter of a brass nozzle over time, acting like liquid sandpaper.
Yeah, they really do.
So if that internal volume is constantly widening, could you theoretically track the physical degradation of your hardware purely by monitoring how much your calibrated flow multiplier drifts over the course of a few months?
Wow. That is a fascinating concept. You absolutely could use the math as a diagnostic tool.
What?
Yeah. If you keep a log and you notice that to get the same solid top layer on the same brand of filament, your required flow ratio is steadily dropping month over month, say from 0.98 down to 0.92, well, it is a massive mathematical red flag that your nozzle orifice is silently widening. The printer needs to push less baseline plastic because the hole is bigger.
It is like the machine is trying to tell you it needs a replacement nozzle through the slicer math alone. You can predict the hardware failure before a print actually ruins itself. I love that perspective. For the full numbers and the detailed calibration guides, see printeray3d.com.